This is the Module 2 of Lecture 18, Deep Neural Networks for Natural Language Text. Okay, so in the Module 1, we finished like natural language applications and also this important component in natural language processing pipelines. So now let's see what are the solutions deep learning provided for those components. So this is a roadmap of what I will cover in the Module 2. So what I will first talk about before deep learning NLP, so the roughly how people handle this, and then talk about like roughly in like it's got popular in 2013 but got proposed much earlier than that, is this word embedding or Word2Vec type of representation. That's the first step. And then after Word2Vec, people so that's just basic word representation, right? And then after on top of Word2Vec, I think in start from 2013 and then get popular in 2014 is this using recurrent neural networks to compose words together. And then this most notable one is LSTM, and then later people extend them into a encoder-decoder formulation, which is called Seq2Seq model. And then recently, I think start from 2016, and then this self-attention based formulation kind of becomes so popular, it almost kind of replaced LSTM based formulation through this formulation just using only attention, so self-attention based. And then really the most recently is people transformer itself is also just a encoder-decoder pipeline type of model on top of the self-attention. And then very recently is people only use the encoder or the decoder part of transformer, and then adding this various kinds of unsupervised or self-supervised loss formulation. The most notable one is those like a masked formulation to learn a better language model. So we already mentioned the language model is a very important component in natural language processing pipeline, right? It modeled the dependencies of words and its neighborhood. So with the current self-supervision based neural language model, it enabled so exciting and state-of-the-art performance of deep learning on many tasks, almost all tasks for the NLP that we covered in the Module 1. All right, let's get started. So the basics. So there's some issue like when you handle the natural language processing. Let's just first see just the text classification or sentiment analysis task. So let's look at this. There are two sentences here. The first is the food is not good, and then second is the book, the wonderful book is really a pleasure to read. So one is going to thumb down, the other going to thumb up. So your natural language classifier needs to handle both, but very clearly you can tell, I mean, they're not the same length, and it's very rare to see, I mean, like natural language texts are the same length, right? So then people, like the first solution we actually talk about in our naive-based text modules is, I mean, we convert this into a backward words representation because that gives us a fixed dimensional vector. So that's very classic, and then yeah, that's actually pretty good. They are a very good baselines for many tasks. For example, the sentiment analysis task, it give very reasonable performance, and like the classic retrieval task. I mean, classic, just like you have a keywords, you try to search, or multiple keywords, try to search like a Google type. For those applications, backward word representation, it's kind of dominated for many years to give the good performance. So backward words representation. But backward words representation are not will not work for many of other NLP tasks. For example, let's use machine translation as example. So for example, in this case, I just have the food is good, and the other is like this food is very, very good. I try to use Google translators to translate into French. I mean, let's just think about, can you even use backup words to do this? There's no way, right? Because backup words removes positions. It removes, it removes like word position information. It also cannot represent like word composition if that's a unigram based backup word representation. But in machine translation, we have to know this food is good and this food is very, very good. I mean, you cannot just remove it because in backup words there's only one variable. How do you decide? I mean, like in this case, where to put this, right? I mean, it's just yeah. So this backup word representation doesn't work for many NLP tasks. Like this is one case, or maybe part of speech tagging, part of speech tree. You just have to keep the word positions as it is. So then the thing is, how do people handle that? So let's look at, so how do you represent a word? I mean, this is related to if I want to use deep learning to solve all of the NLP tasks. So all of the NLP tasks, just like XLNet, I mean, solves like many possible vision tasks, right? So we want to find this like kind of one model, one end-to-end really powerful model can do many NLP tasks, right? So this is the goal. It's what deep learning is good at. So you first need to represent a word. How do you represent it? So they are symbolic. They are symbolic, discrete symbols, right? We actually mentioned about how to represent symbolic symbols in the previous lectures when we, I think when we talk about multi-class classification. The most classic is just this one-hot vector representation. So you just have a binary vector and the length is the vocabulary. The 1 is at the position of the word, and the rest is the 0 that represent that word is there. And then for every position, you have a word basic representation, and then you really represent your sentence as it really is, and then replacing every position into that one hot vector representation. So this creates extremely high dimensional, extremely sparse representation, and it's very difficult to handle. So then like these pioneers, a few deep learning pioneers then propose this idea is, okay, so that's extremely high dimensional and super sparse. Can we project the words into a lower dimensional embedding space? They call it distributional word embedding space, that in that space and the words, the position of the word actually have some kind of semantic meanings. So the previous one-hot representation also has issues. They don't really represent meaning at all because all the words, the differences between each other is actually two. Yeah, if you do like a minus type, if you in the one hot, it's like W1 minus W2 because there's only one position is 1, right? Then you do L1 norm. Yeah, every all possible pairwise distance is 2 in this one hot case. It doesn't work. So in this distributional word embedding, we project into a low dimensional space, and if the words are semantically similar, and we want them to be positionally also close. That's interesting, right? So, for example, this swimming and swam are very close to each other, but their distance kind of similar to walking to walked, man and women, and king and queen, and then just there are so many type of possible relationships you can reflect into a distance of points in that distributional embedding space. So this is the fundamental idea called Word2Vec. So there are many different kinds of Word2Vec models. I mean, very notable one are the 2014 GLOVE model and the 2017 FastText from Facebook. GLOVE was from Stanford. So basically, you can, so this is actually representing, this is just a like one hot representation, and then this is your words, like this is your input. Send the film is a palpably vivo genius, right? So you convert this in, you convert each word into a embedding. So we actually reflect it into this vector form, and then after this, and then you and then just perform other type of applications. So we hope this distributional word embedding captures a lot of background knowledge or biases or inductive biases inside your language. So, and this is extremely powerful, like, and then, but however, if you think about it, this still doesn't solve the variable length issue, right? Because I'm representing each word into its word embedding, but my sentence is still variable length. And it also doesn't compose, because the blob and FastText previous word embedding base, it's just all the, as long as that word is there, it doesn't matter what position it really is, it matches to the same word embedding. So for example, if I have a very here, a very here, and then a very in the W4 and W5, the EW4 and EW5 will be the same vector. So normally this vector is like, the beginning is like 50, now it's actually much longer, but it doesn't capture positions. So then people start actually try to revise it is, so the first thing people try to revise is, so this type of representation that it's not contextual. So can we make it contextual? That's the classic work called Elmo, and later got further revised called BERT. So to get contextual type of word embedding representation. So we will talk about them later. So let's first just keep this variable length issue, right? So we have each word, we got a vector, just a vector, fixed dimensional vector representation, but still my sentence or my piece of text are still variable length, right? It doesn't capture composition of positionally related, so the neighborhood words into, how do you move from word embedding representation into phrase representation, into sentence representation, into maybe article representation. All right, so that's actually the next the current recurrent neural network, why it's got popular. So let's move there. So so after word embedding, people accept it as a norm in was one of the components in deep learning. And then the next question is a variable length type of composition among the words, right? And recurrent neural network got a lot of attention by then. So recurrent neural networks are networks with loops in them, allowing the information to persist. So this is like the difficult to read. So you can think about it's just, so you have a like so you can roll out a recurrent neural networks into this format. It can handle variable length of input. So for each element of your input, you feed into this cell. So one of the, into that component, it predicts this contextual representation from the X0 representation into H0. And then it passes this memory of what X0 you just passed into the next rollout. And the next, like, actually you can, so this is your first word, and then you can input your second word. After you, while you input your second word, it's second word, the cell will consider what just passed to my current cell, and then make a compositional decision to generate a revised H1. So you can think about H1 memorize both the X0 at X1. It's a composition. And then so on and so forth. You can think about HT is a composition, is like a memorization, historical memorization of everything has been fed so far. So from X0 to XT. So yeah, so that's a little overclaiming of the type of the length of the memory recurrent neural network can memorize, but that's the original design spirit. Yeah, so RNN, the most notable RNN is the LSTM, was invented in 1997. And then there are multiple important idea is so because the vanishing gradient issue of RNN, so the gradient issue of RNN, so the LSTM like have a few gates try to control what to pass, what to not pass from history. So which is a very elegant design, and then it's get popular in I think in 2014 because it has a lot of very incredible good success by applying in multiple language tasks. So it was applied in machine translation task in 2014, question answering task, speech recognition, handwriting prediction, opinion mining. So so that's make LSTM very popular in the NLP field because of this multiple like very successful performance number. And then let's see. So the equation wise, I will not talk about it because we have a short class. But essentially, you can like this is the basic equation. So let's look at here. So this is let's see, this is HT and XT. So as I said, I mean the purpose it's the overall design is H4 kind of memorize everything covered so far. But how do that do it? It's doing in a recurrent manner. So assuming H3 covered everything x0, x1 onto x2 plus x3, and then we just pass H3 and x4, and then we use this to generate H4, and this is recurrent, right? And of course there are few gates, much more complicated equation I don't talk about here, but this is essentially the most important like how the embedding got passed from the history to my current point. So if we think about the differences of recurrent neural networks and the traditional feed-forward neural networks, it's really the differences is really just this loop, and this loop can help RNN model dynamic temporal dependencies because it really I'm predicting my next step using my previous step and my current input, right? Of course, I'm modeling the temporal dependencies. So, and if you think from a computational graph angle, the units forms a directed chain graph, which exactly is the text data in its original raw form. And each unit uses the recent history and current input in modeling the next units, the representation. So it can be used for many tasks. So for example, in this case is this part of speech tagging. So I try to tag Bob into subject, into noun, and made into verb, a book collection into noun phrase. This is actually a noun phrase. And actually this task it's a tagging task, right? I'm tagging each word on my sentence. And in fact, this task can be solved by convolution nets too, and people actually use conv nets to solve it. So let's look at this. And a very classic work is called Charles CNN from Facebook, and it could give you really good performance too. And at that time, there's also this bi-LSTM, so this kind of RNN. So we can actually tell it recurrent neural networks has a direction, right? Because you have to know what direction is the history. So people have the left to right, and also with another right to left together, and they observe this kind of bi-LSTM perform better in the sequential task. So all right, so it's essentially we just convert the current word using the embedding of my neighbors, using my history, right? If you have bi, you have the history on the left. You also have the if you have bi-LSTM, you have a LSTM model the history from the left. You have another LSTM model the history from the right, right? All right, so but that type of formulation, it's actually not enough. So we talk about, yeah, so it can model this variable length, right? But in fact, I mean, there are many tasks requires it's not fixed output. So in the previous case, if we look at this part of speech tagging, my output is just this dictionary of part of speech tags is fixed. And for every window, for every word, I'm just predicting to a fixed dimensional output. But there are many NLP tasks, and their output is also not. This is like the variable length output issues. So for example, machine translation, my output is also variable length. In question answering, my output is variable length. In natural language generation, my output is also variable length, right? So how to handle that? I mean, then people realize RNN can be used for model those tasks too. So it can model variable length input. It also can model variable length output. And that's a very classic, it's a very important milestone called Seq2Seq model. So essentially, I'm modeling my input using a RNN. Yeah, that's we already know. In the part of speech tagging, we can do that too. And the novel part is for the output, it's also modeled by another RNN. So in this case, it's a Germany to English translation. So this is a Germany RNN, and this is a English RNN. And if you can still remember what we covered in this encoder-decoder formulation is, so encoder is original X encoded into H, and then H encoded into another X hat. And so Seq2Seq is not entirely this old autoencoder-decoder, vanilla autoencoder-decoder, but it has that workflow. So I'm using a RNN to project X into H, and then now I'm projecting from H into X prime. So it's not original X, but it's a relevant X prime in this case. Or maybe actually, in fact, because output I can even write as a Y, right? So this is a encoder-decoder formulation, and of course loss function is slightly different, not a reconstruction loss anymore. I'm going to talk about it later. All right, so encoder, decoder, encoder RN, and decoder RN, I think that's exactly what I'm talking about in the next slide. So in machine translation, input is a sequence of words. So encoder is on the source language and decoder is on the target language. Here we use two LSTMs, and there's an encoder LSTM on Germany and a decoder LSTM on English. All right, yeah. And this is extremely important model that people extend this Seq2Seq sequence-to-sequence formulation into many, many other tasks, has both input and output like variable length, or even not. So given the source sentence, we learn a optimal representation, and we try to predict the target sentence. And here, I mean, if the task is paraphrase generation, for example, maybe dialogue, the task is not just about accurate prediction. We also want diversified prediction, especially in the natural language generation task. For example, like in dialogue, so you know French, and then how would a person answer or agent answer? So this agent can answer, maybe if you have only a standard, it's yes, I know French, right? But there are many different ways to say that. And for example, this one saying, sure do. My mom's from Canada, right? Yeah, that's really, really interesting. So there's no just one answer in the output. The output is much more dynamic. So can the sequence-to-sequence model this? And it's a very interesting topic. Okay, so let's summarize. Recurrent neural networks can handle many to one. So this is more like sentiment classification, classic task, like many to one. I mean, you just summarize everything, assuming this last embedding memorize everything passed into it. It can handle many to many, So this many-to-many is like machine translation. And this many-to-many, you can think about more like a part of speech tagging, right? Because I want to tag each word into a different output, but they have the same length. This one-to-many is more like a generation task, right? So I want to just use one, maybe Z, to generate a good answer, a good description. So that's one-to-many. Yeah, I talk about it. All right, so again, so this many-to-many, essentially the many-to-many is an encoder-decoder formulation, and this encoder-decoder sequence-to-sequence model is extremely important and has so many applications. We talk about machine translation, we talk about dialogue generation. So this figure actually shows you in this email conversational type, right? So you have an email, and then how do you respond? What do you respond? More like the more general dialogue setting. Okay, so last thing to talk in this LSTM is something called contextual embedding. So this is a work called ELMO. It's it's a very popular model. People always talk about it, so I want you to know. So essentially, I mean, ELMO trying to solve. So we talk in the previous is the language RNN solved this variable length composition issue, right? And then people further combine the LSTM to and the basic word embedding to get a better embedding. So this is what they say as a contextual embedding, which is one of the issues people kind of criticize a glove or the FastText type of embedding because they are not contextually sensitive. So the ELMO essentially has just two LSTMs, and one is from left to right, and the other is from right to left. And then a words embedding is a concatenation of original embedding with the left to right generate embedding, and that right to left generate embedding. And this is actually proved to it's much more dynamic, provide this contextual embedding. All right. Okay, so we finished the recurrent subsections in our like architecture on natural language models, and now let's move to this attention on much more recent advances.